Welcome to Data Streaming Summit 2025. Please welcome to the stage founder and CEO of StreamNative, Sijie.
Good morning, everyone. Welcome to the second in-person Data Streaming Summit. For people who don't know Data Streaming Summit, prior to that, it's called Posa Summit. We changed the format last year to bring more technology into this conference. So if you are in data streaming spaces, you generally facing kind of three big challenges there. So if you want to do data streaming in the public cloud, your expenses in cloud is pretty expensive. If you want to get data from streaming into Iceberg, you'll be facing the challenges there is streams in Lakehouse are kind of still two silos. And obviously, everyone is talking about AI agent. The needs of real-time AI is actually true. So with these big challenges also bring in big opportunities. So we need new architecture that is able to scale, that is able, while you scale, is able to kind of crush the cost. We need to find a way to bridge streaming and analytics together so you can see consistent data along the entire data lifecycle. And lastly, when we're moving from microservices to AI agent, there's a need of shifting the infrastructure to support AI agent. So today, we kind of put all these three big opportunities together, putting the kind of agenda to see how we can tackle all these challenges there. And here's the schedule. So we get started with a keynote from 9 to 11. And after 11, it will be a breakout session until 5. We'll come back on this room for a closing panel discussion. We happen to have like 6 industry experts on the stage to talking about what is the future of data streaming in general. Can one architecture rule the entire data streaming use cases or not? And after that, we welcome everyone to stay at the end. There's a happy hour. So before get started, I want to say a big thank you to all the program committee. Without them, we are not able to putting this agenda together. They help us create the entire agenda for open multi-tech conference. So hope everyone would enjoy the schedule today. Thank you to every speakers. Without your production lessons and ideas, we are not able to kind of attract many of the attendees to the conference. And lastly, I want to thank you to all the sponsors and community partners. This is a conference intentionally to be multi-tech, so it's not just about Kafka only. It's about Kafka, Posa, Flink, Iceberg, along the entire life cycle of your streaming data. So you can hear different opinions from different vendors, different partners. If you got a chance, stop by the booth and talk to them. So without kind of seeing me talking here, I want to kind of kick off the first big challenges that we are facing is how we can leverage the innovations to scale your data streaming architecture and reducing the cost. With that, I want to welcome Matteo Merli, co-creators and PMC chair of Apache Posa, co-founder and CTO of StreamNative, to the stage. He will kick off the first section.
Hi, thank you, Sijie, for the introduction. So actually today, I want to start by taking a small step back here. So last year on this stage, we were showing this graphic to illustrate why we started building Ursa. And we say using this as kind of like a motivation, like all the rationale behind all the choices. So we started by looking at all these problems that people had been facing with Kafka during the years around the interzone data transfer. You want to avoid crossing the easy boundaries to avoid paying that hefty cost. And going down to the disk-based replication. So if broker had to be talking to other broker to do data replication, they also have to cross the AZ boundaries. And moving on the overprovisioned compute. So on the overprovisioned compute, you can think that the architecture is monolithic and very rigid, so it kind of forces you naturally to having to have a much bigger cluster and waste resources in order to support a use case that could be actually solved by and supported by a much more smaller cluster. And if you move downstream, like when you want to get data out and transformed and be processed, what people have been doing most of the time is using different connectors. So connectors have lots of overheads. Namely, you have extra compute that you have to run for this connector, but you also have extra network traffic and extra interzone cost for that. And finally, when you get the data into different places, you're having data duplication. So you have additional costs there. So these are kind of all these areas where we identified and tried to settle to solve with Ursa. But we were not the only one. So in the industry, it had been a trend in the last couple of years to kind of like tackle these problems in different ways with different ideas, different approaches. But we can kind of group these into a few macro areas, right? The first one is like a disk-less, serverless. So several systems have been created to tackle this problem by using object storage as a primary storage. So you kind of like avoid this disk-based replication. And also you have leaderless to avoid like clients having to cross the AZ boundary to talk with brokers. So this is like the first area. Second one is like Lakehouse native. So we've seen that many users want to have their data into Lakehouse. That's kind of like a premium. OK, I have my stream. I want to have this available in Lakehouse in the simplest possible way. I don't want to run ETL. I don't want to run any pipeline to do it. I don't want to run like a batch job to do it. I just want to have my stream and immediately available in a Lakehouse with zero ETL. And in this case, the stream table duality, it can seem like a very abstract concept, but it actually resonates a lot with users. So users actually get it. OK, I have my streams, all the events. I can also see that as a table that is updated in real time. So it's like a really powerful concept. And this integration, this tightly coupling between streaming and Lakehouse, I think has been very powerful and a lot of innovation going there. And finally, I really like this third category. It is like going beyond the partition. I really look forward where we can get partitions out of the picture. This is really a concept that doesn't help the user. It doesn't really resonate with the user. It's just like a gimmick for us as system developers to make things scalable. But it's something that we started years ago approaching in Pulsar with the key share subscriptions in order to kind of like break down the delivery and the one consumer per partition kind of delivery with the order. But I'm really happy that there is more exciting work that is going on, especially at with the LinkedIn, with the Northgard team. And with that, I'm really happy to invite Honor, who's the tech lead for the LinkedIn Northgard team, to explain us what the work they did. So Honor, thank you.
Thank you. Is this on? OK, cool. Great. Hey, everyone, I'm Honor. And today we'll be talking about Northgard, scalable log storage at LinkedIn. So to give you some background, log storage is used quite a lot at LinkedIn for things like logging, metrics, tracing, as well as like stream processing, data lake import-export, as well as like database replication and like AI use cases. And there's more use cases as well. And we're operating at quite large scale. So we're doing over 32 trillion records a day, over 17 petabytes a day, over 400,000 topics. And that's all being run over a fleet of around 10,000 brokers. And we kind of subdivide that among like 150 clusters today. But with that scale came challenges, namely for scalability we were running into use cases where we were hitting the metadata limits of Kafka clusters, and that made us stand up more and more clusters to the point where we ended up having these 150 clusters. But now that you have these 150 clusters, it's difficult to operate them. And that's especially true in Kafka, where the unit of replication is the partition, which is a very heavyweight unit of replication. And that means that you could have multiple hot partitions or heavyweight partitions land on the same broker. And that could lead to skew in resource utilization. And so that meant that we had to develop tools like cruise control to balance the clusters. And that's another thing that we need to operate, right? Another challenge is availability. So with partitions as this heavyweight unit of replication, that means that broker failures lead to windows of degraded availability. So when a failure happens, you're effectively on the clock to quickly replace that replica before more than fail, and potentially leading to produce consume unavailability. And we also had use cases that wanted stronger durability as well. And to address these challenges, we've designed and implemented Northguard, a log storage system with a focus on scalability and operability. And we had a bunch of goals in designing Northguard. I'm not going to read over all of them right now, but there's going to be a strong emphasis on scalability, operability, availability. OK, and one way to think about the design is in terms of the data and the metadata. So let's go over the data now. At the bottom of the abstraction layers, we have the record. And a record is just the most granular unit of data to be read or written. And it's comprised of headers, key, and a value. And those are just bytes, right? And we could sequence these records into a segment. And a segment is like the unit of replication, meaning that a segment is what has a replica set assigned to it. And a segment can either be active, meaning that it's appendable, or it can be sealed, meaning you cannot append to it anymore, it's immutable. And we could sequence these segments into a range. And this range is just Northguard's version of the log abstraction. So it's a log plus some ownership of some chunk of a key space, let's say. And like a segment, the range itself can be active, meaning that it could have an active segment at the end of the range, or meaning that the range itself is appendable because it has an appendable active segment at the end, or the range could be sealed, meaning it cannot have an active segment at the end of that log. So the range is immutable. You can no longer write to it. And we could split or merge these ranges, and in order to do that, we seal the range first. So for example, here, let's say that we have range R1, and we want to split the range into ranges R2 and R3. We would first seal R1 before creating R2 and R3. And let's say we want to merge some ranges. So let's say we want to merge range R4 and R5 into R6. We'll first seal R4 and R5 before creating R6. And so we have this collection of ranges now that cover this full key space, and collectively we refer to this as the topic. OK. So with all that, one key benefit of having this segment abstraction that subdivides that log is that we could do log striping. Log striping is maybe a bit of a misnomer. It's essentially just chunking up this log. But effectively what we're doing is, let's say that we have this range R1, and it has segments S1, S2, and S3. These segments are replicated. Let's say it's replicated 3 ways. And we have these brokers, which are like these kind of gray boxes. And let's say that we've added a new broker at the end. And what we would like is to be able to use that broker easily, right? So in due time, segment S3 at the end of the range is going to eventually seal, which means that we're going to create a new segment S4. And when we create that segment S4, that's now an opportunity to decide a new replica set, which means that there's a good chance that that replica set might land on the new broker. That's really nice for a couple of reasons. One reason is that this lends itself to self-balancing clusters. And the second reason is that when we add brokers to the cluster, those new brokers can get used immediately without having to move pre-existing data off of old brokers onto the new broker. So that's really nice from an operations standpoint. OK. And when it comes to the metadata, at the bottom, we have the vnode. The vnode is a fault-tolerant replicated state machine. It's like a very thin layer over Raft, which we're using under the hood. And basically what we're doing with this vnode is we assign like a shard of the cluster's overall metadata to that vnode. So this metadata might mean like the topic metadata, range metadata, or segment metadata. And we could assign some responsibilities to that vnode, and that's done by the coordinator of that vnode. The coordinator is just one-to-one mapping of the leader of that vnode, meaning the leader of the underlying Raft group. And what the coordinator does is essentially like all the business logic associated with that metadata. So it's basically like doing all the business logic of the metadata for that vnode. And this might include, like, for example, it's in charge of performing like the range split or merge, for example, or it's in charge of creating new segments and sealing the old ones, for example. OK, so with the vnode and coordinator abstractions, we could scale this out now, right? So we could have many vnodes in the cluster. And the way that we've done this is that we kind of organize it into a hash ring. Essentially, the state of the cluster is mapped into a certain part of this ring using consistent hashing. And the vnode also has a position on this ring. And wherever the metadata lands on that ring gets a corresponding vnode that owns that region, right? So the vnode that owns the region where the metadata lives is how you decide which vnode owns which metadata. We call this abstraction of like all these vnodes in the ring the DSRSM, the dynamically sharded replicated state machine. And one little nuance I want to call out is that the positions of these vnodes are fixed in place. So even though the vnode has a Raft group underlying it, and there might be replicas that come and go, maybe they fail, maybe we add new replicas, that doesn't change the position of that vnode. OK. And yeah, so the collection of the vnodes cover the full ring. OK. And for evaluation, when we look at scalability, so when it comes to the data, in Kafka, the log abstraction that it has, the partitions, are bounded by the machine disk capacity. Now, that's not entirely true with remote storage, but the way that we've been running it at LinkedIn, that is the case. And this is in contrast with Northgard, where the log abstraction that we have, that the range is bounded by the cluster's overall disk capacity. And for the metadata control plane, Kafka is bottlenecked by a single controller operating the cluster, and behind that, there's a single replicated state machine. And it gets stressed at millions of partition replicas. Whereas in Northgard, we have n of these coordinators, or vnodes, right? And in reality, that's like over 100 of them in a cluster. And behind those vnodes, there's n of these replicated state machines. And it's doing just fine at the millions of replicas scale. And when it comes to metadata distribution, the way that Kafka distributes its metadata, essentially every broker in the cluster gets all the topic metadata. That doesn't really scale well. Whereas in Northguard, we give very minimal state to all the brokers in the cluster. So the only global metadata that all the brokers know about are like which brokers are alive or dead, what are their hosts and host import information, as well as what are all the vnodes in the cluster and who is like the current leader of that vnode, that kind of thing. So we don't globally distribute the topics, range, or segment metadata. That's local to the vnode, always. And when it comes to cluster size, Kafka has centralized group membership, heart beating to the controller, whereas Northguard uses scalable, gossip-based group membership protocol based on Swim. OK. And when it comes to operability, like I said earlier, we're running Kafka with like 150 clusters. There's some pros and cons to running few versus many clusters, but at Northguard, we think we could bring that down to 3 to 12 clusters. We could potentially go down to 1, but there's benefits to having more than 1. So that's kind of why we have more than 1. For balanced data distribution perspective, for Kafka, it relies on an external service to keep the cluster balanced. At LinkedIn, we've been using cruise control, which we developed. And in Northguard, the data distribution is balanced by design through the log extracting that we have. And when it comes to metadata distribution, this concept doesn't exist in Kafka because there is no sharded metadata. But in Northguard, again, it's balanced by design. We ensure that like all the replicas are like well distributed for all the vnodes in the cluster. And when it comes to adding brokers, in Kafka, again, you need an external service like cruise control to move existing data onto the new broker to keep the cluster balanced. And that's a lot of data movement and a lot of operations that we'd like to not have. Whereas in Northguard, there's no need to move existing data onto new brokers. It will just naturally show up in a couple seconds. Okay. And as for availability, consistency, durability, performance, when it comes to availability, we see that Kafka produce degrades as replicas fail. And again, that's kind of due to that on-the-clock concept I mentioned earlier, where you need to quickly ensure that replicas get replaced before more of them fail. Whereas in Northguard, when replicas fail for the active segment, we just seal it, create a new one. And basically, there's just instant producer failover to the new segment. So we get that benefit from the log striping. And when it comes to consistency, again, due to that heavyweight partition issue in Kafka and the on-the-clock nature of restoring the replication factor, that means that while it's replicating, there's a risk of further failures, which means that we could potentially halt the produce availability if enough fail. So that means that we're kind of forced to make a trade-off more often than we would like to between consistency and availability. Whereas in Northguard, because when we fail, when a replica fails, we just seal it, make a new one. Basically, we are in much less of an urgent need to make this trade-off between consistency and availability. So we actually don't make that trade-off. Like we just choose consistency. And for durability, when you get an ACK in Kafka, there isn't a guarantee that it's been durably written to disk yet, right? So that's due to how it lazily syncs to disk on its replicas. And the way that we've been running at LinkedIn, it lazily syncs every 10 seconds or 20,000 records. In Northgard, we get much stronger durability guarantees. So when you get an ACK as a producer, you know that it's already been f-synced on all the replicas. And we're doing that f-sync every 10 milliseconds or 20,000 records or 10 megabytes, whatever happens first. And we're able to do all these higher availability, higher consistency, higher durability while meeting LinkedIn's SLOs for Kafka and with better durability. Yep. And none of this could have been possible without our team. And for what's next, we're migrating more traffic to Northgard. And we're going to continue to work on performance improvements, have more low latency offerings, geo-redundant storage, and we're going to try to open source it. OK. And yeah, LinkedIn's hiring. If you like large-scale infra, find me after the keynote. And yeah, that's it. Matteo, back to you.
Thank you, Ono, for giving us a glimpse into LinkedIn approach. And it's really inspiring to see this effort to rebuild such a core infrastructure from ground up. I know it's not easy, and there's a lot of work, a lot of effort put into it. But I also like to see that there's a lot of validation that the biggest Kafka user have to be kind of rethinking a lot of the initial assumption, to design a system that could go beyond what Kafka was initially designed to do. And I'm also very, very pleased to see that a lot of concepts are also things that we did in Pulsar many years ago, and this segment-based, also durability, and also the newest approach, the newest things we did with the Oxia for metadata, for scalable metadata. These all concepts are very similar in the two systems. So, but in a similar way, we asked in StreamNative, what is the how can we tackle these cost and scaling problems for everyone, for all our users? And Ursa has been our answer. The Ursa engine, which is a next generation streaming engine, which is fully Kafka compatible, but it was designed to ground up to be cloud native and cost efficient. So last year, we announced the first product preview, but earlier this year, we announced GA, and right now it's really production proven. We have proven this in the most demanding environment, so it's really ready for prime time. And I'm also very proud to announce that Ursa, our paper on Ursa has been selected as the best industry paper this year at VLDB, so this is a very prestigious award. And it's kind of validates all the hard work that the team has put into designing, building, and productionizing Ursa in the last years. So we're also very happy because there were a lot of very strong papers from very big companies this year, and some of which are here today and presenting. So we really love the good competition, but we are very happy of this award. So if you haven't read the paper, you can use the QR code to access the paper. One other thing we did earlier this year has been benchmarking Ursa. So we took a use case of a box of 5 gigabytes per second workload, and I can measure the cost around different Kafka-like implementations. So from a traditional open source Kafka to other vendors, and different flavors of Kafka. So with open source Kafka, basically the cost difference, Ursa is 95% cheaper than open source Kafka and other Kafka vendors, mostly because around a reduction of cost in the interzone data transfer, but also the reduced amount of compute resources because of the over-provisioning that you have to do in Kafka, and also a removal of all the costs associated with this base replication and duplicate the data copies. So it's really a very big difference, and this difference also applies to more low-cost Kafka vendors that have been using also object storage. There are many ways of how you can use object storage and how you can optimize. So that is also a very big validation that what we've been doing is on the right track, and it also has been validated externally by our friends at Databricks. So there's that too. So we couldn't be happier on how quickly we were able to kind of build Ursa and get it to production and get it to users. So now the next question is that how can we get all our existing users that are using classic Ursa clusters into take advantage on the Ursa advantages. So what we actually did is that we kind of packaged Ursa as a self-contained component, and that we can plug it into the classic Ursa clusters. So now you can select different storage classes, and you can select whether you want to continue to use the existing topic format, or you can just use a topic that is in the Ursa storage format and take advantage of that. So this kind of give you a seamless transition from classic into Ursa. And it's really seamless and self-paced, so you're kind of minimizing any risk on these migrations, or there's no migration actually. But that also means that we can have Ursa available on all our deployment types. So you can have Ursa on BYOC and on dedicated cluster, and also on serverless. So that's kind of available everywhere. And start using that either with classic or with Ursa storage. So to summarize, Ursa is the truly one and only Lakehouse native storage engine that is available on all our deployment types, but it's also able to support all the use cases. So you can use the object store-based write-ahead log for like a cost optimizes workloads, but you can also use the disk-based write-ahead log for latency optimized. So with disk-based write-ahead log, you can get the advantage of supporting all the existing classic Pulsar with low latency workloads, more OLTP kind of workloads. And, but it is the same way that the data will eventually make its way into the Lakehouse storage. So it's kind of consistent, unified, and you always have this data flowing into Lakehouse, but with different profiles in terms of cost and latency based on the write-ahead log. And talking about not write-ahead log, but Lakehouse native, I want to call on the stage Kundan, who has been like doing all the work with our partners like Databricks and our customers like Motorq in order to enable Ursa and Lakehouse. So please, Kundan.
Hello all, good morning, good to see you all. So it's great to see the storage capabilities from Ursa come to Classic Engine and all the deployment options we have. The beauty about the foundation of Ursa is that it lets us, it enables us to move faster with our innovations with Lakehouse. It helps us move faster with our integrations with different types of integrations which are available, particularly around how we want to stream data into open formats, right? So if I were to just give you a recap of, from last year till date, in the beginning of last year, we actually announced the support for Iceberg REST catalog. That was an important milestone for us that helped us move faster with our integrations with some of the other vendors who support REST catalog as well. Then quickly we added support for Delta Lake in Unity Catalog. And Delta Lake is a mature open table format which is adopted by thousands of customers. So we're really happy to bring that to our customers. And quickly after that, we were able to roll out support for Snowflake Open Catalog and Amazon S3 tables, because both of them are based on Iceberg REST catalog specification, right? So it's been a great year with all these capabilities now available for our customers, where they can easily stream data from StreamNative Cloud to their favorite lakehouses. But we're not done for this year yet, so I'm super happy to announce that we are now supporting managed Iceberg tables in Unity Catalog, and this will be something which will be available now for our customers to start from today. So, awesome. I'd like to redirect that round of applause to Databricks, our partner who we worked very closely with to roll out this integration to our customers. So Delta Lake has always been available, and now with the support of Iceberg, customers have choice to choose their favorite open table format of how actually they want to stream data to their Lakehouse. So within StreamNative Cloud, essentially, it's very simple now for you to choose how you want to stream your data to your favorite destination Lakehouse, right? All you have to do with a few clicks, you can just stream your topics as tables. Now, to demonstrate the new capability of being able to stream Iceberg tables with topics data as Iceberg tables, I'd like to actually show you a quick demo. So Acme Commerce is an online retailer who is interested in building a data platform which is cost-efficient, scalable, and it serves the needs of all their internal data teams. And Danny and Anna are part of that team. They're part of actually the data team who are catering to all the internal requirements. So the responsibility of Danny is to kind of set up a data platform, as I mentioned, which is really efficient, serves different teams from operational teams to analytics teams. And Anna is actually one of those teams. Anna is going to consume the data which is going to be produced in the platform, right? So now let's just go through that journey of how Danny and Anna are going to work together to kind of set up this platform. So within StreamNative Cloud, basically, as you enable your Acme Commerce application to stream all your data from different sources, whether it's connectors or like coming through different custom applications, they will all show up actually within the core platform. And each of these data sets are holding some significant importance to the respective lines of businesses. So there's product information, there's orders, customers. All the information is something which this platform is designed to support. So typically, there are different ways in which you can stream data into a platform. So picture that you are using a custom application to place an order online. Your order information could have all kinds of information, but typically, it just doesn't trigger one piece of information. When you place an order, it's just the information about the order which starts, and then there's a whole range of other data which comes along with it as to who's the customer who shipped this data, or other, like who's placed the order for this product, what is the payment method used for this order. All those details actually get pushed through the events. So now let's go through the experience of Danny to see how he's going to set up this data platform to receive all this data and serve their internal teams, right? So for that, I'm going to request our AV team to roll the first demo video, please. So this is the experience of Danny using StreamNative Cloud to set up the data platform and receive all the commerce data. So once you're in StreamNative Cloud, the first thing I would do is actually register a catalog, which is basically going to create a connection to your Lakehouse repository. In this case, my target destination is Databricks Unity catalog, so I'm going to choose Databricks Unity for Iceberg. Quickly fill in all the details, including authentication, and I just verify my credentials, and now this catalog is registered successfully, and it's available to be used in a cluster. Now, Danny is going to create a cluster. There are many options available for Danny. The quickest way to start is actually a serverless cluster, now that we have Ursa storage and Lakehouse capabilities available in this. So I'm quickly going to fill in all the details, my instance name, my underlying cloud service provider, and all the other details. So with a matter of few clicks, I can choose my destination and choose the pre-registered catalog, ensure this setting applies to all topics, so I'm streaming it, all of them as external tables, which will be managed by Databricks, and then I just finish it. So in a matter of few seconds, this cluster will be created. In this case, I've shown you the creation of serverless cluster because now it has the new Ursa storage capabilities and Lakehouse storage capabilities, but for the rest of the demo, I'd like to use the BYOC deployment, which is one of our popular deployments. So typically, you would choose BYOC while creating it. But in this case, I'm going to switch to a pre-created cluster, which Danny had already created. So here, within the cluster, you can find all details like the access points of your Kafka broker, your schema registry. Configuration will ensure that you selected and wired your catalog to the right destination. And now this cluster is pretty much ready. So at this point, I don't have any data. So what you'll notice is I'll enable all the applications to stream this data to this platform. And as the data starts coming into the platform, all kinds of orders are shipping. These topics will start populating into the platform, right? Now, quickly, Danny is going to click around to ensure things are looking good. Well, this is the right schema for this topic. Let me take a sneak peek on the data. Is this looking good? And Danny's going to click around to make sure the orders are getting placed fine, and this is a valid data set which is getting produced. And after that, quickly verification of, okay, the topics are mapped to the right set of schemas in the schema registry. So this is all set. Now the data is already flowing into the destination storage bucket. So let's go to AWS console now to see how that data is showing up there as Iceberg tables. So within the storage bucket, you'll notice there are folders, and all the Iceberg tables, the topics are showing up as Iceberg tables. There are 6 folders for the 6 topics we had. And within this folder is where all the magic is, all the work which our partners are doing, helping us with. So this is where you can find all the manifest files of your Iceberg table, the Parquet file comprising of all the data. I also want to ensure that the data is also showing up in Databricks and not just landing in the S3 bucket. So now Danny is going to log into Databricks and explore the catalog where I'm seeing all the topics showing up as tables, readily available for the other teams to consume. So for the rest of the so this is, to summarize again quickly, Danny was able to set up a data platform where essentially the platform is ready to receive data from different sources, and it is configured to stream all the data as Iceberg tables in a destination, Databricks Unity catalog. So for the rest of the story, to continue the rest of the story, I'd like to invite Michelle on the stage from Databricks, who is going to talk about the rest of the things. Michelle, welcome.
Thank you. Hello. Hi, everyone. I'm Michelle. I'm a product manager at Databricks. I work on all of our open Lakehouse offerings. I'm very excited because today I'm going to talk to you about, why does a catalog matter and what does unified governance across the streaming Lakehouse mean for us here at Databricks? All right, so just as a quick reminder, a little bit about Databricks. We're a data and AI company. Our mission is to democratize data and AI, which is just a very simple, a very fancy way of saying that we want to make it super simple to work with and build and derive insights from all of your data and AI assets. But the problem today is that it's not simple. So it's actually really difficult. I talked to a bunch of customers as a product manager, and they all say the same thing, which is that their architecture is super complex, it's messy, they're dealing with all these fragmented governance across their operational data estate, their analytics estate, all of their AI assets. They're all using all these different tools and technologies. So this is a little bit about what that looked like. At any mature organization, you'll see that they're using dozens of tools for maybe ETL, for data warehousing, for machine learning, now for Gen AI, also for streaming. And this kind of creates this super complex web of high costs. Maybe you're duplicating data or duplicating your storage costs or egress costs or something like that across all of these different tools. And then this kind of leads to a lot of lock-in, where lock-in means that your data is siloed. So that's kind of what these little blue circles sort of represent, is the idea that frequently in many of these tools and platforms, your data is stored in a proprietary storage format with proprietary metadata, and it's kind of just housed in that one tool. And then furthermore, governance is also siloed across all of these different tools. So there's not sort of this single end-to-end, for example, like lineage or view or observability across all these platforms. So in many cases, our customers will find themselves either needing to glue together many technologies or just flying blind. Okay, so one of the first things that we at Databricks did is actually we are the category creator for the Lakehouse, leading the development of open table formats like Delta Lake, and then now also, of course, we have first-class support for Iceberg. And so it's this idea that, hey, let's break down those silos, all of those blue circles that are across all these different tools. Let's take that, let's just put that into the customer-owned commodity cheap object storage in an open table format that any engine or tool can be able to integrate with and read and write. So it's all in this open data lake. And so now the Lakehouse has really taken off. A bunch of vendors have adopted it. OK, so now what's the next challenge? It's now this piece around unified governance. And so this is what I'm going to talk about a little bit more today, as well as demoing, which is what does unified governance mean to us? So just to double click, right, we just saw Kundan and even just pulled up the AWS console, right? All your data, it's just files in object storage that any sort of engine can read and write to, whether it's like ingestion or streaming or you're doing ETL or analytics workloads. It's all operating on this same copy of data. And that's what the Lakehouse architecture is sort of defined by. But the missing link between the two is the catalog, which provides this unified governance and which also helps to provide this sort of like single pane of glass through which you can actually view and manage and govern all of your data and AI assets. And so what does unified governance mean to us? It means two things. The first is unified governance for all assets, so governing all tables in both open table formats like Delta Lake and Iceberg, being able to also govern your unstructured data in files, your AI models, and even dashboards. And then the second is that we also believe that governance needs to extend beyond the traditional sort of access control and auditing capabilities that traditional catalogs sort of stick in, and said that, hey, this catalog needs to provide this single pane of glass through which you're doing all of your search and discovery, end-to-end lineage, having a single definition of what a metric means, like in business semantics, or even doing things like quality monitoring, so starting to bring in this idea of data intelligence, where we can actually apply AI with our knowledge of all those metadata and workloads and stuff like that to be able to produce insights for you about your data. OK, so with that, now I've talked a little bit about unified governance. This is kind of how our thesis of how Unity Catalog can actually govern that streaming lakehouse and actually bridge, especially with this integration with StreamNative, the sort of streaming and analytics data estates. OK, so now we're going to go pick up that demo right where we left off with Kundan. So now I'm going to put on my hat as Anna, who's a data analyst who wants to make sure that I'm getting insights from my data and also doing so in a way that's governed and compliant. All right, so let's head over to the demo. Oh, yeah, OK, great, yeah. So here we're going to see me as Anna discovering, governing and querying some data in Databricks. So we're starting off here in the Catalog Explorer. This is where you can view all of the data and AI assets in your organization. As you can see here, there's the schema and some of these tables that just landed from StreamNative. And you can see that they are all landing as managed Iceberg tables. For all managed tables, whether Delta Lake or Iceberg, Unity Catalog automatically optimizes the data layout to provide you the best query performance. And then let's go take a look at now the sample data, just to make sure that everything looks right. OK, yep, it seems like we have a bunch of data here that landed from StreamNative. Amazing. Let me go quickly explore this. So I want to see, maybe just quickly see what the shape of the data is. It looks like actually I can leverage Genie for this, which is this box right here at the top. There's a few sample queries that it provides, so maybe let me just use one of those, finding the top 10 cities by customer count. And so what Genie does is it allows me to explore this data in natural language. So it actually automatically generates that SQL query, and then you can see some of these results land. And it's all actually within the context right here in the Catalog Explorer. So I showed an example that had the sample query, but of course you can actually type any sort of prompt that you want or any query that you want into Genie to explore that data and derive some insights. OK, so now as we're looking at the sample data, I do see a problem, which is that this data contains PII, specifically email addresses and social security numbers, and those are stored in plain text, which is definitely not good. And so as a good citizen, I want to make sure this is governed. So Unity Catalog makes it super easy to apply governance at scale with attribute-based access control. So you can see here that my administrator actually already set up policies at the catalog level, which this table inherited, for masking the emails and social security numbers for columns which are tagged as such. So if I go back here over to the overview, I can actually go add these governed tags to those specific columns. So for this first one, for SSN, I'll actually add the PII tag, and then I'll actually tag this as SSN. And then behind the scenes, what this is going to do is actually it's going to trigger that mask SSN function. I will do the same for the email column. Again, we'll add that PII tag and the email tag. Amazing. And so these tags have been automatically applied. It's actually super simple. This is all behind the scenes. You'll see that the masking functions automatically kick in. And then now, any user, including myself, should not be able to see this data unmasked. So you can see that now the email addresses and social security numbers are masked out. And it's all super easy without needing to write a bunch of super complex rules or duplicate policies across a bunch of different tables and keep those consistent. All right. So just to kind of conclude and pull this together, I'll just recap just both what Kundan and I just showed you, which is with this integration between StreamNative and Databricks, we're really excited that StreamNative now supports not just Delta tables, but also writing to managed Iceberg tables in Unity Catalog, demoed how attribute-based access control can enable fine-grained security and governance at scale, and how together this is providing unified governance across that streaming lakehouse. All right. So with that, I will now pass it over to Ashwin from Motorq.
Hi everyone, and thank you, Michelle. Hi everyone, Ashwin here, from co-founder and CTO at Motorq. It's a great pleasure to be here at the Data Streaming Summit. At Motorq, we built one of the most advanced connected vehicle intelligent platforms by partnering with leading auto OEMs and serving some of the top organizations across the industries that we impact. We turn data into intelligence and intelligent into actions. We help our customers make smarter, faster decisions and manage their ecosystem effectively. Talking about connected cars, the OEM connectivity and value realization has accelerated over time. When we started Motorq, only 20% of new vehicles were connected. But over time, more OEMs, auto OEMs have joined the party. And if you look now, about 95% of the new vehicles are connected. How does the data flow? We ingest data from auto OEMs and aftermarket partners. We process, normalize, and generate insights in near real time and in batch manner. And our customers are able to get the insights through various interfaces that we built, optimized for different needs. We serve fleets, fleet management companies, dealership software companies, and many other industries in the transportation space. So as this system has evolved, there has been more and more demands on the system in terms of performance, scale, latency, cost, and so on. And for our next-gen architecture, these are some of the requirements that we had. Elastic scaling was very important. We wanted to be able to handle varying loads effectively, cost-efficient manner. We'd like a system which takes care of these things by itself. Native multi-tenancy support was very important to us. We did not want to spend time on workload isolation. We didn't want to reinvent workload isolation, tenant-level resource controls, and generally we wanted to reduce our development overhead. We wanted to have a more cost-efficient system over time to be able to transfer the benefits to our customers. On the Lakehouse side, we wanted lower latency, and we really were looking forward for native ingestion to Lakehouses. We felt that should be solved at a lower level platform side. We wanted to generally spend more time on innovation and less time on these platform overheads. We were able to get a lot of these benefits from managed Pulsar and Ursa. So with the newer architecture, we are able to publish into Pulsar, and Ursa is able to deliver these streams directly into the Lakehouse, into the Iceberg tables. Internal and external use cases are able to access these insights and intelligence through the Iceberg REST catalog. We do have our own internal Iceberg maintenance jobs right now, but over time they should move to native support. These are some of the benefits we were able to get from managed Pulsar. We were able to get native multi-tenancy support, which we really were looking forward for, so we don't have to worry about those isolation problems. They also benefit our cost. Elastic scaling was important to us. We wanted support to handle varying workloads. Features like key shared subscription types really helped us. That with other features really helped us achieve elastic scalability. Overall, we were able to reduce the cost by 50%. And special thanks to StreamNative for their expertise, great support, and very quick response times. Moving to the Ursa and Lakehouse, we were able to get much lower latency. Our earlier systems in a cost target manner, we used to take close to an hour for syncs, but we are able to do the same in minutes, which much lower costs. In fact, our ingestion latencies are, our ingestion costs are around 60% lower with the newer architecture. And we generally have a much simpler pipeline now. We don't have to write custom connectors. We don't have to write custom ETL jobs or syncs jobs. We love the native Lakehouse writes that we have now. And schema registry support has also been a great benefit to us, from contracts to early error detection to general improving the quality of our system with lesser effort from our side. Over time, we believe that the industry is becoming more proactive, more intelligence into the system, becoming more action-oriented, and more autonomous workflows in coming times. All this said, we are hiring. Please talk to us if you'd be interested in these problems. That said, I'd like to invite Neng to join us on stage to talk more about streaming in this world of AI and agents.
Thank you, Ashwin, for sharing how Motorq is utilizing Pulsar with Ursa storage to tame the Lakehouse integration, and also sharing with us the benefits of the streaming augmented Lakehouse. Hi, everyone. My name is Neng. So I'm the founding member and the director of platform engineering here at StreamNative. So now that we have just explored how StreamNative and Databricks together can unify streaming data and the Lakehouse to help organizations tame the data problems, in the next, we're going to discuss about AI agents and the streaming infrastructures. So probably the first question comes to us as streaming enthusiasts or streaming experts is why streaming matters for AI? Is this a tailwind for streaming industry? So in our view, we feel that in general, the streaming infrastructures can feed timely, fresh events and data to the AI to help spin up the data flywheel. And the highly scalable infrastructures we have built over years to support the ever-growing and the scale of the AI applications, and the loosely coupled architecture to support the quickly evolving and ever-changing business use cases for AI applications, and the enterprise-grade securities we have been enforced to make sure that AI is secure and safe to be used would in general benefit the overall AI applications. But what does it actually look like in the real world? Today, we are very fortunate to have Aravind Suresh, the member of technical staff here at OpenAI, to show how OpenAI builds its streaming infrastructures to support their rapidly growing business and bringing AI to the real world. Let's welcome Aravind.
Hi, everyone. Thanks, Neng, for the introduction. Hi, everyone. I'm Aravind, and I lead the real-time infrastructure team at OpenAI. Excited to be here. And we're going to talk about how we build the streaming infrastructure at OpenAI, right? Before going further, let's talk about why real-time streams actually matter for AI. I think Neng set the stage here, but let's hear it from OpenAI's perspective, right? The first use case, one of the critical use cases at OpenAI that streaming infrastructure powers is basically data flywheel. Now, what is data flywheel? Data flywheel is basically a self-reinforcing loop. So you have products, AI products, and you get a lot of usage from that. And you pull in all of those usage events, metrics, and using that, you end up training better models. Now, eventually, when models become better, that kind of drives product usage even further. And this flywheel loop keeps spinning faster and faster. Now, stream infrastructure is very critical to this loop. So product events, metrics, all of that flow via Kafka. Kafka is the durable storage for that. And Flink is used for real-time processing. So you can do all sorts of aggregations, joins, transformations on top of all of this data. And that kind of helps influence, make better models. And the loop keeps spinning. A lot of critical user inputs like which response do you like? Like sometimes you would have seen ChatGPT give you 2 responses and you would have been asked to rate one over the other. All these kinds of things help us, all these user inputs help us to build models that respond to you in a way that is better for our users, right? So this is one example. Another example is experimentation. So in today's AI world, fast experimentation is very important for model progress. So, and in today's AI world, models are being trained in a highly distributed and asynchronous manner. So think about it, right? There are a lot of experiments that keep going on a daily basis, and you need to understand how an experiment is going. Without stream infrastructure, what we have seen is engineers and researchers build a lot of bespoke, custom tooling to basically understand where their experiment is going. Like, what are the things that they need to tweak, or is this even the right direction, and things like that. But with stream infrastructure, we have noticed that all these experiment events can flow via streams, maybe through Kafka, and then you can use Flink jobs to aggregate and visualize all of these experiments just to understand what the latest state is. This kind of forms the bread and butter of all our researchers and engineers at OpenAI. The outcome of this is you have a fast, more efficient experimentation loop, and in turn, it ends up in better AI products and systems. It's not just use cases like this. There are a lot of product flows that is powered through stream infrastructure. I can go over a few examples. Model distillation is one of them. So just for some context, model distillation is the process of training a smaller and efficient model based on the responses of larger models. Now, guess what is the data pipe for streaming all of this data? That is Kafka. Another example is ChatGPT conversations, search. So I think all the conversations end up flowing through our stream infrastructure and are finally indexed that allow users to basically search over all their historical conversations. It's only a matter of time if you're a regular ChatGPT user, you will have hundreds or even thousands of conversations, and at some point you'd be like, oh, I want to look up this conversation 6 months back. Stream infrastructure powers that. Another example is ChatGPT memory. So conversations end up flowing through our stream infrastructure, and memories are extracted out of it so that ChatGPT's responses are more tailored towards your usage. It's not just these product flows. There are a lot of core building blocks in the company that end up getting reused throughout different parts of the stack. Here are a few examples, like rate limiters. So rate limiters use Kafka as the single place to publish all the usage events from, like, let's say, different clusters or services into one single place, and Kafka is basically that data pipe. Now, this gives us this unified view across, like, what's the overall usage sliced by some dimensions, and based on that, you can do accurate quota enforcement. Another example of a building block is like counters, like all kinds of counters, API calls per user, per IP, anything like that. Kafka is the data pipe, and Flink is used for aggregations. ML features. So stream infrastructure is used all throughout for any kinds of ML features. At OpenAI, we use the open source framework called Cronn that that makes it easier for our users to basically specify ML feature definitions declaratively. So you can say that count the number of clicks this particular asset gets every 15 minutes or something like that. And Cronn basically ends up generating Flink apps and stuff behind the scenes. This enables our users to, when I say users, it's all product and research use cases at OpenAI. They end up defining ML features easily without worrying about all the infrastructure complexities behind the scenes, right? So having looked at all of these different kinds and shape of use cases, let's just try to bucket them and see what are the different types. Number one, asynchronous processing. So any kind of cases where you want to decouple the producers of data with the consumers, that's where stream infrastructure is very helpful. This is a proven and tested pattern in the industry too. The second thing is like inter-service communication. Anytime service A wants to talk to service B, but doesn't want to rely on service B being up, or it wants the data pipe to be very much reliable, that's where stream infrastructure fits in. The third shape is basically any kind of processing. It could be just stateless consumption. It could be anything stateful, transformations, joins, aggregations. All of these things are things that Flink does it for us. So this is another shape of use case that we see. The last thing is like data warehouse ingestion. Right now at OpenAI, data warehouse ingestion is actually a downstream of Kafka. We were historically using Spark streaming. Now we are moving towards Flink. And this is another shape of use case because ultimately Kafka has a limited retention window. So beyond that, you would still need that data in some cases, and that's when data warehouse ingestion helps. Having understood like the different kinds of use cases at OpenAI, let's take a look at what are the key decision factors. So we're basically going back in time, right? These are all the use cases that are being supported today. So let's go back a year or two and see what were the key decision factors that helped shape our real-time infrastructure. Number one, our users wanted an interface that hides infrastructure complexities. So building AI systems and AI products is a complex and hard problem in its own way. Our users, basically service owners, product builders, they didn't want to worry much about how Kafka works internally or how Flink works. Like, they wanted an interface that abstracts away all these infrastructure complexities. The second thing is we needed resiliency to single region failures. This is a very fair ask, and it became more and more critical as ChatGPT got adopted by hundreds of millions of users. The last thing is we wanted the system to be horizontally scalable. Like as ChatGPT scales, obviously there'll be more events, and we wanted the stream infrastructure to also scale along with it, right? Now, there are multiple ways for you to solve this. Let's take an example of Kafka, right? Like if you want to have a multi-region Kafka setup that solves all of this, I see it going in a few ways. So you could have things like you spin up different Kafka clusters and replicate data between them, and then think about how to do the failovers there and things like that. Another example is, which I've seen in few cases, is basically having stretch clusters, where the Kafka cluster itself runs across multiple regions. Now, all these things were ideas that we discussed, and these are actually more complex, which made us take a step back and think, like, what are we even trying to solve? What do our users want, right? And that's when we made a few key observations, and we chatted with all of our users to figure out what they actually want and what we want to build. We noticed that most OpenAI use cases do not need ordering. And most OpenAI use cases do not need key partitioning or anything. And none of them required Kafka transactions. So we leveraged all of these inputs, and we came up with a simpler architecture that scaled. Obviously, there are a bunch of trade-offs, there are a bunch of gotchas, we'll talk about that. But what we ended up building was, we ended up building a bunch of proxies. So this is the first proxy that we built. Just some context, the namings in all of our team is basically behind light and science. So the proxies are called Prism because events, we refer to them as photons. Prism disperses events across multiple clusters, so that's the idea here. So you basically have Kafka producers that end up talking to Photon, which is the client, and then that ends up talking to Prism, which is our proxy, and that basically balances publishes across multiple Kafka clusters. So let's say there are 3 clusters, and you publish 30 messages. Around 10 of them go to each of these clusters. So it's just regular load balancing, which means you end up losing a bunch of things like partitioning, you lose a bunch of things like ordering, but most of the use cases did not need it, so this seemed like a viable strategy to pursue. Now you could ask, okay, you publish it to these clusters, what happens on the consumption side? On the consumption side, it's a similar story. We ended up having another proxy, just that we adopted an open source component called uForwarder. It was built and open sourced by Uber. So what we did is, this proxy basically inverts the push and pull paradigms of Kafka. So traditional Kafka consumers end up pulling from Kafka. Here, uForwarder does that pull for you and ends up pushing messages to the downstream Kafka consumers. And the consumers can actually hack a message or mark it as failed, or they can mark it for retry, and then uForwarder handles all those retries for you, and eventually, after a bunch of retries get exhausted, it handles the DL queuing and all of that for you. One key thing to note is we get the benefit of scaling the number of Kafka consumers beyond the number of Kafka partitions you have, because uForwarder basically fans it out to as many pods and replicas of the services of the Kafka consumers that exist. So this is basically the idea that we pursued at OpenAI a year or so back, and let's talk about all the trade-offs, right? Like, obviously, we are throwing a bunch of things that we do not want, so let's talk about them. The first thing is no partitioning. Both our proxies do not support it right now. You could say that I can publish in a key partition way to Kafka. Sure, you could do that, but our consumer-side proxy doesn't honor that too. So because it just fans it out based on, it's just going to pull data from Kafka and just fan it out to different Kafka consumers. So that way, we do not have partitioning support here. The second thing is there is no ordering in Kafka streams. Mainly because there are retries across multiple, like in the sense that messages end up getting split across different clusters. And also on the consumption side, uForwarder kind of throws that out too, because different pods can respond to messages at different pace, which means the third message could get agged before the first message. So you kind of lose ordering there. And the last thing is at least once delivery. There are just so many layers in the stack. There are so many retries. And also on the uForwarder side, there could be duplicates on delivery side too. So there are just retries across the stack. So there are just so many trade-offs. But one thing we noticed is most use cases are open with this. And in the few cases where users were not OK with it, there are meaningful alternatives. An example is, if you wanted partitioning, maybe you could repartition it in downstream. Maybe you can have it push down that logic into Flink or Spark. And also when you need ordering is actually a very hard problem in a distributed system setup. But in the cases that you need ordering, maybe come up with a logical clock, stamp events with a timestamp, and sort based on that in the downstream. It does add a latency bit here and there, but it is just OK for at least the critical use cases. The last thing is for at least once delivery, just do exactly once processing somehow in the downstream. Maybe do deduplication or some notion of idempotent processing, and that's it. So we had a bunch of trade-offs. We had a bunch of ideas, and we chatted with our users. It kind of made sense. And there were meaningful alternatives also for some of these power users. But are these trade-offs worth it? Did it actually work? Yes, it did. And our users actually liked it. Because what we learned through this process is ultimately users want an abstraction that's simple to consume and simple to use. Obviously, there are a bunch of trade-offs that you need to make for this, and which, if people are OK with it, in exchange for that, they get a bunch of other things. They get ease of use. Kafka and Flink is extremely simple to use at OpenAI. It's easy to provision topics. It's easy to start publishing to it. It's easy to write consumers. And this enabled a lot of developer velocity at OpenAI. The second thing is you get reliability. Before the proxies, we had a problem where, so OpenAI, all the development kind of mostly happens in Python. So as you all know, due to GIL, services end up spinning more processes instead of threads, right? Because of that, you will end up making an order of magnitude more, maybe 10x to 50x more number of connections to whatever systems you interact with. It could be databases. It was true for even Kafka brokers. So, but with the proxies, things were more reliable, and we even got benefits like because connection count went down, a single Kafka cluster that flow was more reliable. We also had resiliency to single region single region failures. So that was also, so overall the Kafka published flow became more reliable. The same thing holds true for consumption. The third benefit is scalability. So if you look, since we are just multiplexing your publishers across multiple Kafka clusters, if your throughput doubles, you can just double the number of clusters and things will just work. So the one question I often get when I tell people the story is, OK, fine, this is something that worked out at OpenAI. Do you think it is generalizable? I think there are a few learnings, and there are a few principles that we adopted in this journey, and I think those generalize. One top principle that I would like to share with you all is this. At any point in time, you will have infrastructure teams that need to support a mix of use cases. Some would be simple, classic things that would just work for your stack. Some would just be things that would need a lot of tuning and there would be power use cases. But at any point of time, keep this in mind. Like, always build an infrastructure, always build abstractions that enable this. Simple things should always be possible through that, right? But like, simple things should be simple. Like, it should be easy for users to adopt, and it should be easy for users to use, because there's no point building infrastructure if nobody's going to use it. But always make sure that complex things should still be possible. This goes back to the meaningful alternatives bit. It's okay to take trade-offs. It's okay to make hard decisions, but always keep in mind that there are meaningful alternatives, at least to keep your power users happy. And this is not something that we just solved with just Kafka, because the proxies were built a year back, and our stack has evolved since then. Did it stand the test of time? Yes, it actually did. At some point, like towards the end of last year, we've had needs for stateful stream processing came up. So Flink enters the picture. And we were able to extend the same setup. So we still adopt the multi-region Kafka topology that's there. And we had a few challenges here and there on like integrating Flink apps, custom Flink source, custom Flink sync. But we were able to make the same ideas work. And this is still the Kafka stack at OpenAI. And later, we also realized that we wanted to do real-time data ingestion. That's when we ended up moving our ingestion systems from Spark to Flink. And building this system, it kind of built upon all the same primitives, and the system just, we were able to extend the same system. So this kind of summarizes to where our journey of stream infrastructure at OpenAI. This is kind of the current stack, a simplified version of it. Now you could ask, like, how is the scale and adoption like? Like, okay, sure, it is successful. Users have adopted it. Let's look at some numbers to confirm. So it's used by every team at OpenAI. All product services use Kafka or Flink one way or the other. The second thing is the growth and scale is immense. It's just 3x every quarter. It comes up with something like 10x every 6 to 7 months. We've already seen 1 or 2 instances of that. So we are right now, the top of mind thing for the team is how to prepare for the next 10x. The third is stream processors. If we just go by how many stream processors there are just over 200 processors. It could be Kafka consumers, it could be Flink apps. It excludes the data ingestion stuff, but there are just 200 plus use cases of stream processors at OpenAI. And also the peak Kafka throughput is around 80 gigabytes per second, which ends up tripling every quarter. And to put this into perspective, this is basically like 10 million YouTube videos or something. If you play them every second, if you play 10 million videos concurrently, this is the amount of data you would stream. So this is all about what is the current state. Let's talk a little bit about what is next for the team. What are our future directions? There are 3 key pillars. The first pillar is like next-gen infrastructure. So as I said, we are thinking about how to make real-time infra work for the next 10x growth, right? Bunch of ideas, tiered storage being one of them. The idea here is how to leverage cloud storage better. The second is diskless Kafka. There's been a lot of chatter around this, especially in the last 6 months to 1 year. There are a lot of talks today in this particular area. So this is something top of mind for the team that we're thinking about. The second thing is autonomous resilience. One thing, if you notice that, like, I think you would have noticed it in your experience too, coming to a scalable design, a design that is horizontally scalable with usage is one thing. And then if it works, sure, you'll be happy. But it's only a matter of time where you end up spinning a lot of clusters. So you'd be happy that the design scales, but you'll have a lot of clusters to deal with. This is kind of a problem there, right? There's just too many clusters. I think Honor also mentioned about this from his LinkedIn experience. There's just too many clusters at some point. Now, how do you solve that problem? Either you do some kind of fundamental re-architecture, but until then, you end up needing things like intelligent control planes to manage all of that. It could be things like provisioning, cluster health, monitoring, all of that. And you kind of need self-healing systems beyond a point, right? Because we noticed that the number of pages our on-call gets kind of increase with the number of clusters. So at some point, yes, we need self-healing systems, and this is something that we have been thinking about. We also noticed that as a part of this, there are a lot of places where AI agents itself can help us to give some time back for the infrastructure teams to go ahead and focus on other things. One example from OpenAI is we noticed that there has been a lot of Flink app development that was going on, but users found it very hard to debug their Flink jobs, like what's the latest state, what is the, if there's a failure, what should I do about it, and things like that. And we noticed that AI agents actually do a pretty good job of that. So we basically integrated AI agents that look at your Flink logs, Flink app information, understands how Flink is deployed at OpenAI, and basically gives recommendations on what to do next. So we've seen that help. So I think this is also something that you can try to see wherever AI agents can help, making users more productive. That's something everyone should explore. The last thing is, I think I called this out already. So data ingestion at OpenAI is still a downstream of Kafka. But there is this trend in the industry. I think we already folks spoke about it in the keynote. There are also multiple talks on this around, can we unify the data silos between streaming and data warehouse? So native data lake ingestion is something that we haven't thought about much so far, but something I think we will think about in the next year or so. So these are basically the future directions for the team. While I'm kind of sure that these are the things that the team would basically look at, I also have a few open questions, which I'd like to just share with all of you as like closing thoughts, right? So these are things that we should just take a step back, forget about all the things that we're working on. Just think about like, okay, there are a lot of AI stuff happening. What are things that at least we should do from an infrastructure perspective? So let's take a step back and think along those lines. So the first thing is, what kind of streaming infrastructure do AI agents even need? Like till now, we have been, in a way, trying to extend whatever current setups we have and trying to see how we can build AI agents or at least empower AI agents use cases and stuff. But let's think about like, if ultimately AI agents are just chatting with each other, do you even need durability in any point? Like, do you need durable data pipes in between them? Like, won't in-memory buffers be sufficient? There are obviously a bunch of solutions that give you, systems that give you these guarantees, but this is something for us to, let's say, think about, right? Because I expect a lot of AI agents to just be chatting with each other in the near future. The second thing is, there are reasoning chains associated with all of these reasoning models. And chain of thought data is actually very large compared to just conversations or anything else. So if all of these reasoning chains, which are very large, if they go through our streaming infrastructure, will it really work? That's also something for us to take a step back and think about. The second thing, this is actually a little bit interesting. So we have talked about infrastructure that heals itself. Like every system that has scaled had some kind of self-healing capabilities with it. And we are talking about infra that heals itself, but we also have AI agents that kind of respond to failures and that can help you in one way or the other. Now, where do you draw that line between an infrastructure that heals itself versus an AI agent that just responds to failures? Maybe the AI agent can do more things, right? So this is also something for us to just keep in mind, maybe think about it as we all build systems. The last thing, this is just a plug for the panel later today. Can one streaming architecture rule them all? So I see a lot of folks here, a lot of use cases, a lot of requirements, a lot of trade-offs, a lot of systems being built, a lot of different architectural decisions made. Now, can just one streaming infrastructure just solve all of them? There's something for us to think about, and I'm not going to talk about this. There's a panel later today where we have exceptional panelists who are going to discuss this and get that clarity for us. With these closing thoughts, I kind of wrap up my session. Thank you all for listening. Back to you, Neng, to talk about AI RAW streaming.
Thank you, Aravind. Yeah, thank you for sharing the impressive streaming architecture behind OpenAI to help us understand the importance of streaming architecture for this AI era. And thank you as well for these intriguing closing thoughts to move to our next section. So in the next, we're actually going to talk about agents and streaming. And probably some of the points may help answer your questions and closing thoughts. So to begin with, I think we need to have a review of how the LLMs and agents has been evolving over the years. Since the inception of ChatGPT, we have seen raw large language models being able to answering people's questions, interacting with users, and as more and more people started to using these amazing large language models, people started to asking for more accurate results, asking for more timely data response. So we started to seeking solutions to improve the large language models, fine-tuned models. And then with the invention of retrieval augmented generation, we are able to do chunking and embeddings with the real-time data and save them and use that as a knowledge base for the foundational large language models to answering all these questions. And then with the inception of model context protocol, MCPs, the models suddenly started to be able to interact with all the existing systems around the world. And with all these, as the model started to getting more and more smart, and the MCP ecosystems continues to grow, more and more tools are available for these models to call. We started to see the agents to be coming into the place. And there are a lot of agent startups nowadays tackling general tasks or vertical areas to help evaluate revolution this whole area. And here at StreamNative, we believe that as the innovation comes in and as the industry grows, eventually we will arrive at a stage that's called autonomous agents. So what's autonomous agents? First of all, it's just an agent with the normal capabilities an agent has, that it will perceive the world around it, accept the signals or the requests from the external world or user input, and you will be able to do reasonings with LLM models to understand the questions, to do plannings for the tasks that it needs to do, and also you will be able to call in some of the tools to take actions as a response or the react to these external worlds. But beyond that, we believe that the event-driven layers will also be needed in order to achieve this autonomous agent stage. So with the enhancement of event-driven architecture, we will be able to loosely couple all those agents around the world, and we will be able to providing the real-time data continuously to the agents so that they can do perception and reasoning and actions. And also with the model of the event-driven, we have asynchronous communications protocols sits in between all those agents so they can react to each other, calling each other, and collaborate together to accomplish the tasks. And eventually, we will be able to do very easy elastic scalabilities to all these agents we have been deployed. With all that said, the challenges for autonomous agents still exist. So there would be very complex streaming infrastructures to tackle with in order to plug in the event-driven capabilities to all these existing agents. And how we insert the real-time data into the agents so that they can react timely, that would be another challenges we'll be having. And also, as you may know, there are a lot of nowadays there are a lot of different flavors of agent frameworks for people to develop their agents, whether that's OpenAI Agents SDK or Google ADK or some of the other agents frameworks like Llama Index or LangChain. Or some of my friends at some kind of agent startups, they would actually do their custom agents purely based on Python. So, and all these agents needs to have the state saved. They need to have proper tool access with the scaling and orchestrations built into the platform. And also the security governance is always the very important things we need to tackle with. So these are the challenges we have seen for autonomous agents. And here at StreamNative, we want to take a step at those questions and trying to imagine how these problems can be solved from a streaming infrastructure perspective so that all these agents can be truly autonomous. So with that said, we are glad to announce that we are going to launch the Orca Agent Engine today. So this agent engine is a new idea that we have been experimenting internally at StreamNative with our users and customers. So what is an agent engine? It's imagine that it's not asking you to redevelop all your working agents from the existing frameworks and then tackle it with the streaming systems. Instead, all you need to do is actually deploy your agents with the streaming infrastructures so that your agents actually sits in between the streams and they can percept, react, and reasoning about all these events happening and collaborate together to handle the ever-changing real-time world. So with that said, we kind of designed instead of asking users to adopting some of the existing architecture, existing systems to their new case, we want to design this agent engine like from scratch with the agent developers like you experience in mind. So we want it to be Pythonic. As you have been already heard from Aravind, that in OpenAI, most of the applications and agents are developed with Python. So we believe this is a common pattern in the agent industry. Everyone loves Python, and they use that to develop all these agents. And we also want the agent developers have the ability to bring their own agents to the streaming platform instead of like changing the already like working existing agents to interact with the streaming systems. So on the streaming side, we want to make sure that the agent engine can actually work with multiple streaming protocols like Kafka and Pulsar. So Pulsar, most of the time, like Kafka is for like data ingestion, and Pulsar can be used for like event streamings. So it has to be like secure and with great governance. And also like all these additional capabilities would not overcome the fundamental abilities we have for the agents. Like they can have the options to choose like models they want. They can call MCP tools as usual, and they have the access to context and memories to do better reasoning and help better understand the users. So these are kind of the design principles we have, and the architecture we have been designed for the agent engine is like this. So sits in the center, it's actually the agent you just developed using your own favorite like agent SDK. And on top of that, we actually wrap it into abstraction so that like the streaming data can be ingested as an input, and the result of the agent can be sent out as an output of the streaming systems. It can also have the abilities to do retrieval from like PostgreSQL and the vector database. And it can also call all kinds of tools available to take actions to the real world, like managing the Kafka Pulsar clusters and talk to other agents or functions available deployed in the clusters, and even calling like external MCP servers to do more complex tasks. And also we will be having like memories and context remembering so that like the agents can do better and better as the time goes, and it has more information about the user or about the request. So with all that said, I would like to invite you to have a demo, take a look at our demo to see how it works actually in the production systems. So we will be beginning with creating a service account that has the proper like permission assigned to this agent to be used later. So this is the newly launched GA StreamNative RBAC systems, so that we can actually like assign proper permissions with the names on the different levels to make sure that the agents we are going to launch have the proper accesses to the system or to all these data. So here, like we assign the created service account, adding the row bindings, and we will be enable this service account to be used in the infrastructures later. So now we are going to take a look at a vibe-coded like a weather agent here. So basically what it does is like querying the open internet for the weathers of a certain given location and return that as a result. So everything looks pretty standard and normal. It's just the OpenAI agent SDK program. So here the fetch weather tool is just getting the information and cache some of the important information and then return the result. And the show cache is another function tool we use to remember some of the informations the agent interacted. And at the bottom, we can just run it with an agent runner. So it looks like pretty normal and standard. You can run it like on your laptop or anywhere just to get the result by interacting with the OpenAI models. And now we are going to deploy that into the cloud. So basically all we need to do is remove the last two lines with the runner so that it only defines the agent and how it works and what other tools it needs to do. We just need to zip that and create a zip file and then do these YAML configurations. So the interesting thing is on the last line, we enable store, and we provide some metadata information to register it as an MCP tool in the whole systems. So we will see how they will be used in the later stage. So with the configuration and with the code and with the service account, we can easily deploy it to the StreamNative cloud with the one-line out command. And we can just start here to querying the agent for informations, like what is the weather in San Francisco. It's not today, but yeah, it's. And also like other cities, like what is the weather like in New York, and then it will also like give you an answer quickly. So we can also restart the agents easily if something is wrong. And the important thing is like once we restart agents, all the in-memory like state has been cleared. We can see that there's no like information processed. But again, still we can ask the agents like what is the history, like what is the last question I asked you, and what is the cache, current cache for the San Francisco cities that we have just interacted. So this actually shows the state store. We are remembering some of the informations in the systems for persistent usage. And we can also easily like update the parallelisms manually or automatically with one line of command change. So here like we are updating that agent to two replicas. And we can see that there are 2 instances up and running, and with the first one, like actually processed the last 2 questions we just asked. So yeah, it's kind of very scalable and remembering everything, and can seamlessly interact with the streaming systems. And here, like this is a second example. Basically, we are trying to let the agent to use all the available MCP tools, like inside the clusters, inside the systems. All we need to do is utilize the agent context object and register tools with the agent. And in the configuration files, we will need to provide the MCP streamable HTTP configurations so the agent knows that where it needs to talk to get all these MCP information and get some of the dynamic update from the MCP service. So we already deployed that. We can now ask the question like, what are the tools available to you? So in addition to some of the additional tools like Pulsar and Kafka, we also have the weather fetcher tools, which is actually the first agent that we have been deployed on the cloud. And we can also ask questions to this new agent that utilizes those weather fetcher tools to get us a result for Los Angeles. So it is, all the agents are actually can talk to each other as long as you register yourself to the systems, and they can utilize the functions or utilize the agents, other agents to work together to deliver the result to the customer. And we also build out agent UI here for the easy exploration of some of the visual like Explorer. We can see that the processing guarantee is at least once here, and we are using the OpenAI SDK to develop this agent. And also there are agent tool configurations. Basically, that's the streamable HTTP configuration we just provided. We can also select some of the tools from the whole overall systems. And then this is some kind of easy user interactions for you to check out how agents looks like and works in the systems. So with that said, we only look at like some of the single agents, but actually really like the Orca engine unlocks a lot of like patterns that we hear from the agent developers that they want. We will be able to have scheduled event and deliver delayed messages processing very easily. So you can have your agents to get the data at 1 hour later or 1 day later, depending on what you need. And since the data is retained in the streaming systems, the data replay and the auto failure retry would be very easy to achieve. And we can also like set the parallelisms as we show in the example demo and do rate limitings for all those agents tasks. And last but not least, we will be having able to like create a mesh of the workflows and agents to work together and calling each other and collaborate to accomplish the tools. Yeah, it's great. And we are excited to share that Orca engine is actually available today for all our StreamNative cloud deployments, including serverless and dedicated and BYOC. Yeah. Yeah, thank you all for listening to this AI agents and the streaming section. And we are looking forward to see streaming technologies to further empower AI. And we would like to invite all of you, all of the streaming experts and the agent developers to work together to help advance this area. And I would like to hand back to our CEO, Sijie, for our next section.
Thank you, Neng. Before that, I was just closing out the morning session. So we get started with kind of 3 big challenges. There is streaming cost is very high. And second, streaming and analytics are kind of siloed to a certain extent. And last, the rise of the AI driving some of the infrastructure changes. As you can see, this is all these three sections are not isolated with each other. They're kind of the entire life cycle from you get started from streaming data into your system, bridging the streaming data with your Lakehouse tables so you can accelerate your insights. And once you have the data in insights, you can empower your agent to processing those data in insights. And you probably hear the same pattern across different breakout sessions. I hope you have enjoyed most of the conversations so far with the keynote speakers, and hope you also can check out different breakout sessions. But before that, we probably would to look ahead where Lakehouse, streaming, and agent AI in general are head towards. We have a special guest today. We are honored to have Databricks co-founder, Chief Architect Reynold join us for a fireside chat about the future of real-time data infrastructure. Welcome, Reynold.
Hey, thank you, Sijie.
Thank you.
Glad to be here.
Yeah. Do you want to maybe say hi to?
Sure, yeah. I was actually in this Grand Hyatt in San Francisco just about 25 minutes ago, getting to the wrong hotel. And then when I asked them, hey, so where is this conference? People asked me, hey, what are you talking about? And then I opened up the website. I'm like, oh, shit. And then, but I'm glad to be here on time.
Yeah. Thank you. I think it's a magic to come from San Francisco downtown to airport within 25 minutes.
It's a testament to the traffic.
It's also light speed.
Exactly.
Okay, so before we get started, we'll probably get we talk in the keynote. We get started talking about streaming, Lakehouse, and a lot of talk is about kind of getting data into Lakehouse. Obviously, Lakehouse is really hard. Especially with the acquisition of Tableau, and Iceberg has become kind of really popular. But really, I want to kind of maybe get started with the first question to step back. I think Databricks, you guys create a category. It's called Lakehouse, and you coin the term of Lakehouse. But what kind of problems that you try to solve with Lakehouse, and what Lakehouse can solve that data lake or warehouse cannot solve?
Yeah, by the way, it might seem sort of evident, obvious these days. Hey, everybody's talking about Lakehouse, but if we just rewind back time about 5 years, back to like late 2019, early 2020, at the time, I think there's always historically, there's two classes of technologies in data in the last like maybe 15 years. There's data lakes, there's data warehouses. And maybe there's even happened to have emerged two kind of strong vendors in each of the space. Like Databricks was started with the data lakes, and maybe before Databricks was like Cloudera and Hortonworks, if you sort of want some archaeology, and then Snowflake emerged as the leading cloud data warehouse vendor, right? The technology was kind of fragmented. If you went into any enterprise, I mean, even today, if you go into a lot of enterprises, you realize, hey, they have maybe one department that operates what they call a data lake, and have another department that operates what they call a data warehouse. And they kind of split their workloads arbitrarily based on largely historic reasons. Often the business intelligence workloads and reporting workloads are more about looking into the past, were stored in the data warehouses. And then a lot of the, pretty much any other workload, it doesn't matter if it's streaming, more heavy data engineering, data science, often about looking sort of forward, predictive, looking forward to the future. They store them in data lakes. And the two paradigms of text were kind of incompatible. And it's kind of very frustrating to a lot of these companies because they realize, hey, depending on my use case, my data are split, and I might or might not have the right data in the right place. And it's incredibly annoying to plumb them through. If you look at what most kind of maybe big tech companies like Google and sort of Meta and all of these companies, you look at their internal infrastructure, there's typically a unified data foundation layer for everything. Like all their data are in there. It doesn't matter what you do. So we just had this idea of sort of at the end of 2019, early 2020, which is, hey, why can't we just unify it? Yes, the off-the-shelf technologies, open source technology back then were not completely there yet. Like it's difficult to run, for example, state-of-the-art BI in sort of data lakes, but we think the tech would get there. So why don't we just propose, hey, we can unify it, and over time we'll work on whatever the gaps is needed, and we'll take, obviously based on our heritage, we're going to take a data lake-centric view of it, but we'll evolve the tech, so over time we can do all of the workloads. And we spent enormous amount of time debating the name. There's Unified Analytics, there's a lot, anyway, there's probably like 2 pages of names that are proposed. At some point, Matteo Zaharia, my co-founder, said, why don't we just call it the Lakehouse? And then every salesperson at Databricks hated it. So we almost didn't use this name. We almost went with a super boring name, Unified Analytics. But at some point, we're like, hey, the Lakehouse, we started talking to some customers. And our CMO, Chief Marketing Officer, actually was it's like, hey, we shouldn't use this name. But then the customer started saying that name. And then before you know it, everybody started talking about the name. And now sort of every company says, hey, we're building a Lakehouse. So the name kind of stuck in a way, so incidentally.
Yeah, I still remember that you guys published a paper to CIDI in 2021.
Yeah.
That is a kind of a really good overview about kind of what is Lakehouse. If you haven't got a chance to read that paper, you should read it. It's a very well-written paper there.
Yeah, so just to make sure it's not complete marketing fluff, we wrote a cider paper.
Yeah.
An actual paper about it.
It's a very technical and also research like style there. Obviously, I think Lakehouse from like a new name became a paradigm, and it also changing a lot of ways how people build system, build tooling, and obviously this is a data streaming summit, it's a data streaming conference, and how do you see like streaming fitting into this Lakehouse paradigm, and how these two systems can work together?
Yeah, so I think if you go back to the cider paper, one of the workloads we talked about that data warehouses traditionally didn't support really well was actually streaming. So before Databricks started, our founding CEO, Jan Stoica, actually had a streaming company, and streaming there does not refer to data streaming, but video streaming. But the actual data infrastructure powering the video streaming was actually a data streaming system, confusingly. So we always sort of thought, hey, streaming would be one of the most important workloads. Everybody wants to be more real time. Yeah. Everybody wants to get up-to-date insights. But streaming is just incredibly complicated as sort of technology to operate, or at least back then. It's getting a lot easier. One of the things one of the key, I would say, differentiation between Lakehouse and data warehouses, hey, that store large amount of, almost all of your data in open storage formats. In the data lake or object stores, right? Cloud object stores are basically the large data lakes out there. We actually thought, hey, there's no, one question we actually asked ourselves back then is that, hey, for the primary technologies operating both on cloud data warehouses and lake houses, were becoming, so all feature some sort of separation of storage and compute, which means if you don't have a lot of workloads, you can shut down your compute. Even down to 0. If you do have workloads, you can now spin them back up. And if you have too much workload, you can have a multiple replica of them operating on top of the shared storage system. And streaming systems were not built that way back then.
Yeah.
And we're just wondering, hey, why not? But then we're very happy just a few years later when we started talking, realized, hey, that's how you're actually designing the whole thing.
But also, I think even you don't kind of purpose build the kind of streaming within the mind, but the Databricks developed a Delta Lake. I think there's one, I also read that Delta Lake paper, there's one kind of strong use cases is how Delta Lake can be used as a messaging queue is because the entire design is pretty like streaming oriented to a certain extent. Yeah. So you already have that mindset kind of built as part of the entire Lakehouse ecosystem.
Yeah, so when Delta was created probably in 2017 or 2018. Yeah, 2017. You remember the history better than I am. It was actually initially created for a specific use case at Apple. I think one of our distinguished engineers actually gave a keynote at Data and I Summit many years ago about it. And the use case was to get all of their network data, network security data, into the data lake. That was before the word Lakehouse was invented. And then they want to be able to run fast analytics on that. And the use case was for security information event management. So if you have, for example, if you realize you have a breach somewhere, you're being under attack, you want to be able to very quickly figure out what's the blast radius. So having up-to-date information was really, really important there. Now, in those use cases, we're not talking about like ultra low latency. They're okay with maybe seconds of delay, sometimes even minutes. But that was baked into the very beginning of Delta's design, which is we're very insistent on a single file commit, which is actually one of the main differences between Iceberg and Delta at the very low level is the single file commit thing. This is just to minimize the latency as much as possible.
Yeah, I saw the single file commit is also coming out in V4 as well. I think there's a consolidation on table formats as well. Speaking of streaming, and also we have open table formats, how do you see these, what kind of the challenges that will be facing, like if we want to bridge these two together? Is it more like a architectural perspective, performance, or is more like a governance, what's your opinion there? Yeah.
Probably pretty much all of the above can be better. I mean, Delta was pretty good from a single file commit perspective. We're bringing the same thing into the Iceberg v4, as you said. There's actually a large debate about it on the community dev list on, hey, do you really need single file commit? How important it is. But I think beyond that, one of the things arguably is that the data lake has won and sort of like open format has won. So I think every message bus wants the ability to land large amount of data quickly into the data lake. And I actually don't think the formats themselves are providing enough primitives. And the reason could be, it doesn't have to be foundational. It could be as simple as, hey, there's actually no good APIs, or there's no good library for you to actually call very easily so you can land a bunch of data in Iceberg or in Delta format. All of the libraries are either at too high level abstraction or too low level abstraction for the actual maybe streaming engines or sort of message buses to implement. So they either couple too much into the protocol, so you have to understand the protocol in order to use it, or they don't give you enough control. I think that's like actually a pretty serious big gap that probably nobody would think about unless you try to go through that journey of like dropping files into the object stores. And then I think governance is also a pretty big part. I think historically, very little attention was paid to governance, maybe like 10, 15 years ago, because people were just trying to cobble together to get things to work. But now once you be able to build some infrastructure, you care a lot about, hey, RBAC, ABAC. And I think that has gotten to a point. If not yet this year, next year will be pretty good for just the Lakehouse itself. But streaming is coming a little bit as an afterthought in many systems. And if you think about it, hey, if you want to spend a lot of time thinking about how to govern your actual data at rest, why shouldn't you think about governing your data in action? Like, what if somebody just goes in and peeks at all the data and then dumps it out, right? That shouldn't be the case, maybe like 3 or 4 years from now.
Yeah, and that's why I think we kind of are very excited kind of working with your team on kind of integrating with Unity Catalog. I think Unity Catalog is kind of putting that in the right direction to govern not just table data, also AI assets there. One thing you kind of mentioned about the kind of the gaps, some of the abstraction are too high level, either too coupled with protocol, and there's some of the abstraction is too low level, is not enough. And obviously, I think one to pull back is the streaming to Iceberg, streaming to Lakehouse is very popular nowadays. There's so many like solutions, and people might be using Connector, using Flink Job, Spark Job, and also all the Kafka vendors, including us, is kind of getting into the motion of Iceberg topic to a certain extent to get build in the Iceberg or Lakehouse storage engine within the messaging broker. I think there's so many different solutions. That reminds me the fragmentation that data lake or warehouse that you have been seeing like 5 years ago, 6 years ago. Do you see if there's any emerging like a standard protocol that the entire industry is kind of pushing towards to? What's your view on this?
Yeah, I think there's a lot of, I'm of mixed minds here. I both think that there's an incredible amount of value to sort of standardize, for example, storage technology, standardize on 1 or 2 different formats. And if they're similar enough, it doesn't matter if they're sort of different or not, as long as you can very quickly actually convert them. But at the same time, I also feel like Parquet itself is incredibly outdated.
Yes, for
and
sure.
It's still, it's something that the Parquet authors invented the thing without actually understanding deeply, when they were pretty young and inexperienced. They were incredibly smart and great engineers, and I work with them all the time. But in practice, they actually, the reality is they didn't understand how important it would become. And it became accidental success. I actually think there's a lot of innovation that can be done even at the Parquet layer. And I would be shocked if 10 years from now, we're still sitting here talking about, hey, Parquet 1.0 or V2 encoding is what we're dealing with today, 10 years from now. I think a lot of those, like for example, Parquet requires writing a footer at the end, which is not necessarily great for streaming workloads.
Yeah.
Like many of this, it was just put in so very early on without understanding and without having seen all the workloads out there. It's not because the people are dumb, it's because they haven't seen it yet. And now the world is very different. Now it is also true, the more data we have written, the more difficult it is to upgrade the format. But I really hope industry as a whole will be able to work together. And we certainly will spend also effort there to actually improve the format. I think it should be pretty easy to get a 2x improvement in compression or another 2x improvement in decoding speed, and certainly can make streaming way better.
Yeah, makes sense. So probably talk quite a lot about kind of Lakehouse streaming and probably switch a little bit gear. I think everyone loves talk about AI.
Yeah.
It's a must there. So how do you see, like Databricks also announced like Agent Bricks like earlier this year. How do you see the role of streaming in Lakehouse in playing supporting agents there?
Yeah, at the end of the day, there's a lot of, agents are very generic words, a lot of things you can do with it. But one of the things is the more data it has, typically, depending on what the purpose of the agent is, but the more data the agent have access to, the more better decision making it could be doing or the better things it could be suggesting. And so I think the world largely has maybe 4 buckets of data. There's the operational database data. This is like the data you put in your OLTP databases, MySQL, Postgres, Oracle, and all that. And those are, in a way, it's probably a smallest amount, but the most important business data, right? And then there's all the analytics data, which often actually includes a copy of the OLTP data. Might or might not go through a message bus.
Yeah.
And there's a tremendous amount of operational data that typically go through some sort of streaming, either through a message bus or people dropping it directly into S3 and then load it back in. This is like the 3rd bucket. And there's a 4th bucket, which is all the unstructured data. And here, I don't mean logs, but actually like images, random emails, documents, stuff like that. Historically, largely useless because there's no good way to analyze them, but with LLMs, it's actually becoming, LLMs are incredibly good at analyzing piles of text. So you want the 4 buckets of data as input to agents, and that's incredibly important. The other thing I think often sort of, it's more on if you want agents to make actions, or even if you want to evaluate agents, which are less talked about, because it's very obvious, hey, you want more data. But you want the ability to, so agents are not trustworthy, but they're just like humans. One of the things that's really changing with the industry is that because the LLMs and the coding agents and whatever agents can do a lot these days, so you want to actually leverage it. But you can't fully trust it. You don't want it to wipe your production database. You don't want it to like maybe delete your data or so maybe write the wrong merge statement, and then now your data's been sort of corrupted. But then you do want the agents to be able to sort of figure out what to do and make the recommendations. How do you do that? Well, you want to have the capability in every layer of the stack, effectively branching and replay, right? The reason we're very comfortable with LLM coding is because what's the worst that could happen in coding? You restore your Git to a specific point in time because you can branch it off. Basically, you can snapshot. Well, in the case of Git, everything's always a commit hash that you can restore back to. So even if the agents start going crazy and committing crazy stuff, you can restore it back to a point of safety. And then you can run many, many coding agents in parallel to compete for the best solution, and then pick that solution and merge back in. That exists to some extent with data infrastructure. Actually, streaming is actually one of the better infrastructure here because streaming had always had the checkpoint replay infrastructure built in from the beginning for fault tolerance. So agents can leverage that to, hey, let me get all the data. If it doesn't work out, let me just replay it. But a lot of other data sources don't have that capability. Or even if they don't, it takes an incredibly long time to actually complete that checkpointing and snapshotting and replaying. So I think one of the pretty exciting changes that we'll have to do in order for agents to work really well is this ability of basically the Git equivalent for almost everything.
I think you bring up a kind of really good categorization about kind of 4 buckets of the data, and also bring up these kind of Git-like requirements for the infrastructure. So like, to you, like, what kind of for all the kind of people here, whether you're building your own in-house system or vendor building your product, what do you think about the next generation of the infrastructure will look like? There is like, everyone would just like more like branching, checkpointing capability, more like a lake-based neon that is, you have the ability to checkpointing things and roll back and giving agent to explore different possibility there. How do you feel about that?
I think, maybe I'll talk about meta point first, which is how do I think about the future? I think the future is, if you think about system design and system optimization, so infrastructure optimizations, in the past, vast majority of the effort went into, hey, how do I make sure a specific workload is performant enough, right? It's fast enough, it's cheap enough, and then if I make sure every individual workload is cheap enough in aggregate, I will be okay. So I try to pick maybe the fastest thing to run this query or sort of the highest throughput message bus and all that. I don't think any of those would go away, but I think what we historically didn't look at are dimensions of, hey, how fast can I provision something? How fast can I scale something up and something down? How fast can I do this kind of branching and maybe branching it off to like 1,000 different things? Because in the past, maybe I have only 10 engineers that would need to worry about it. So it's OK to do this manually, and it's OK, it takes a day to branch off a database because I need to do a hard copy. But if you have 1,000 agents that work at this speed of, it's not speed of light, but let's say it can speed of token generation, that it can do a lot in a matter of minutes or hours. And then you might have thousands of them working on the same problem. Then there's a lot of attention needs to be paid to how easy it is to do all of those. And the way to think about it is, hey, it's actually not very different from humans doing it, except just faster working humans that can also communicate at higher bandwidth. So in the case of humans, there's a point of mystical man-months, right? Which is, hey, the more people you throw at the problem, maybe you actually slow down the project. And that's largely because of communication. The more human you add, like pairwise communications n square. So the more human you add, the more time are spent on communications. Agents have less of that problem. It still has a problem, but less of the problem because the factor, the throughput, the constant factor is a lot bigger, or the inverse of a constant factor is a lot bigger because agents can communicate. They are machine-to-machine communication. Yeah. A bisectional bandwidth between any pairs of machines in the data center could go anywhere from 10 gigabit at the low end to like 100 gigabit at the high end. They communicate far faster than humans. So you can have way more agents coordinating. I might be talking a little bit like sci-fi here, but it's going to happen. And as a result, a lot of the dimensions that historically you wouldn't have to worry about because you simply don't have that many humans to stress those dimensions will become increasingly more important. It's probably going to be the differentiation of one system over another for the next decade.
Makes sense. So we talked quite a lot about the future of these kind of changes that is probably happening. And I think there's quite a lot of attendees coming from different enterprises. What's kind of your advice to them from like prepare for these changes, like any toolings, skills, or any architecture kind of design principles that you can kind of share with the audience here?
Yeah, I think one is I don't think anything Europe learned will go away. So it's probably just not how, at least the fundamental principles of technology, they're not going to go away. Those things are still incredibly useful. Yeah. I do think when it comes to sort of AI and agents, we are in this interesting time that there's both a lot of skepticism and a lot of overly optimistic sentiment about it. Yeah. I think the best way to think about it is probably we tend to overestimate the progress of things in the short term, but then underestimate it in the long term. I think it's incredibly important to learn and to experiment and keep a very open mind with new technologies, just given how fast things are shifting. And because I see this over and over again, especially with senior people, they look at some new thing, they have a preconceived notion of it, and then they try it, and the moment they hit any roadblock, they're like, hey, this thing sucks. I'm never going to touch it. The reality is that thing is actually improving, and then also being able to use that thing. It doesn't matter if it's AI or if it's Ursa. Yeah. It takes time to acquire that skill of using that thing and leveraging that thing effectively also. So I think it's incredibly important to keep an open mind. I mean, people that show up here are probably on the more bleeding edge and are more open to it. Yeah. But then at the same time, don't sort of maybe fall into the traps and hypes completely of, hey, the whole world is going to change overnight. Like it will take a while also. But what you want to be is you want to be ready for that change, and you want to understand what's coming. And that you can only get it by trying.
Cool. Awesome. Thank you for all the kind of insights that you have been sharing with the audience. And I think that's probably the entire kind of fireside chat. And I'll probably take a couple of minutes break, and then the breakout session will probably get started soon. And thank you, everyone, for coming here, and hope you enjoy the conversation with your peers. Thank you, everyone.
Thank you.